Section 5.3 Graphs of Polynomial Functions. In this section, you're going to recognize characteristics of graphs of polynomial functions, use factoring to find zeros of polynomial functions, identify zeros and their multiplicities, determine end behavior, understand the relationship between degree and turning points, graph polynomial functions. Here is a warm-up activity. So in this warm-up activity, you're going to learn how to factor either by pulling the greatest common factor or with other methods. So the first one here, you need to factor this. I noticed immediately that I can pull 3 out as a common factor. So if you divide now, 3 divided by 3 is 1. 1 times x is x. Plus 18 divided by 3 is 6. So that is the factored form for that expression. The second expression, I noticed that I can pull 2. And I can also pull x squared out. So if I do that, I will end up with 2x cubed divided by 2x squared is just x, minus 8 divided by 2 is 4, x squared divided by x squared is 1. So that is the factored form for the second one. The third one here, I'm going to do some trick here. I'm going to divide this expression into 2. So I will factor by regrouping. I will regroup the first 2 terms together. And then I will regroup the second 2 terms together. Now, from the first binomial, I'm going to pull x squared out. So I will end up with x plus 3. And then I will pull negative 9 from the second binomial, this one. And I will end up with x plus 3. Notice how now I have these are common factors, so I can pull them out as a common factor. What I will have left, I will have x squared minus 9. However, x squared minus 9 can be factored further. So I'm going to say x plus 3. And then I know that x squared minus 9 can be factored into x plus 3 times x minus 3. And that is the full factorization of that one. D, I can factor because this is basically quadratic. So I'm going to use the AC method. So AC is equal to negative 12. I need their 2 numbers. Their product is negative 12. Their sum is positive 1. That is negative 4. That is, negative 3 and positive 4. So I'm going to rewrite this as 2x squared plus 4x minus 3x minus 6. And then I will factor by regrouping. So I will regroup the first 2 together. And then I will regroup the second 2 terms together. Now from the first binomial, I will pull 2x out. So I will end up with x plus 2. And then I will pull negative 3 out from the second one. So if I pull negative 3, I will end up with x plus 2 as well. And again, notice that these are the same. So I'm going to pull that out as a common factor. What that will give me, if I divide by that, I will get 2x minus 3. And that is the full factorization of number D. Now, let's say we have this equation right here of the 4th power. X to the 4th minus 5x squared plus 4. How do we solve this? We're going to treat it as a quadratic. So if we substitute, we can assume that x squared is equal to another variable, let's say a, and we rewrite the equation. So if we rewrite the equation, this is going to be a squared minus 5a plus 4 equals 0. Now I'm going to factor because this is now quadratic. So I will have a and a. I need 2 numbers. Their product is 4. Their sum is negative 5. That is negative 4 and negative 1. If I solve here, a minus 1 equals 0, it will give me a equals to 1, but a is x squared equals to 1. That will lead to x equals to positive and negative 1. So that is the first part. Second part, a minus 4 equals 0 will lead to a equals 4, but a is x squared because we assumed that from the beginning. So that will lead to x equals positive and negative 2. So we have 4 solutions for this equation. So equation like that can be treated as quadratic. The trick here is to make x squared equals to another variable and then treat it as quadratic, solve it as quadratic, but don't forget that the variable that we assumed is actually x squared. It is not the final answer. So with these skills refreshed, we are ready to dive into the content of this section. The first thing we're going to learn is to recognize the characteristics of graphs of polynomial functions. We know that polynomial functions of degrees 2 or more have graphs that do not have sharp corners. Recall that these types of graphs are called smooth curves. Polynomial functions also display graphs that have no breaks. So the curves that have no breaks and they're smooth, we call them continuous. Here is a question. Do all polynomial functions have as their domain all real numbers? Why or why not? The basic answer to that is yes. So the answer is yes, because polynomial functions are continuous and defined for all of the real numbers. Recall the general form of the polynomial functions, which is f of x equals to a sub n, x to the n plus a sub n minus 1, x to the n minus 1, plus a sub 0. So, but because of this form, there are no restrictions such as the square root or division by 0 that would limit the domain. Therefore, any real number can be substituted for x in the polynomial function without causing undefined results. As you notice here, there are no denominators or square roots in the expression of polynomial functions. So that is why the domain is all of the real numbers. So we know that. Factoring, how can we find the zeros of polynomial functions? In order to find the zeros of polynomial functions, we're going to set the function equals to 0. If the polynomial function can be factored, then we can set each factor equal to 0 and solve. Just similar to what we did for this problem right here, when we factored and then we set each factor equal to 0 and solved. So we're basically using previous skills that we learned from previous chapters in order to solve these equations and find the zeros for the polynomials. We can use this method to find the x-intercepts because at the x-intercepts we find the input when the output value is 0. So if the polynomial function is a quadratic function, we can solve it using factoring or the quadratic formula. However, higher degrees polynomials are a little bit harder to solve, so we're going to limit ourselves to just the 3 cases. The first case is the polynomial can be factored using known methods such as greatest common factor and trinomial factoring or factoring by regrouping and etc. The second case is the polynomial is given in factored form, which is the most common one. And then if we can use the technology to determine the intercepts. So we're going to limit ourselves to these 3 polynomials or 3 cases only, identifying zeros and their multiplicities. Graphs behave differently at various x-intercepts. Sometimes the graphs will cross over the horizontal axis at an intercept. Other times the graph will touch the horizontal axis and bounce off. Suppose, for example, we graph the function shown, f of x equals to x plus 3 times x minus 2 all squared times x plus 1 all cubed. You will end up with this graph right here. Notice how the x-intercept where x is equal to -3, the first one here, is the solution of the first factor equals to 0. So we make the first factor equals to 0 and solve, and we get the first intercept at -3. Notice how the graph passes directly through the x-intercept. It passes directly through the x-intercept. And I am going to also mention that the power of that factor is 1. So I want you to link the power with the behavior of the function at that intercept. You notice here that the factor is linear. So it has a degree 1, like I mentioned here. So the behavior near the intercept is going to look like the behavior of a line. That's why you can see the behavior looks like the behavior of a line. It passes directly through the intercept. We call this a single zero. We call this a single zero because the 0 corresponds to a single factor of the function. The x-intercept where x is equal to 2, which is this one right here, is the repeated solution of the equation x minus 2 all squared equals to 0. And notice how the factor has a power of 2. The graph touches the x-axis at the intercept and changes direction or bounces off. As you can see here, the behavior, it touches and bounces. The factor is quadratic, meaning it is of a degree 2. So the behavior near the intercept is like that of a quadratic. It bounces off of the horizontal axis at the intercept. So we have basically 2 of these. But we do not repeat the solution. The factor is repeated. As you can see, this is the factor. X minus 2 appears twice. The number of times a given factor appears in a factored form of the equation of a polynomial is called the multiplicity. The 0 associated with this factor, x equals to 2, has multiplicity of 2 because the factor occurs twice. So if it has a multiplicity of 2, the behavior of the graph is going to touch and bounce near the intercept point, and it's going to behave similar to a quadratic. And we say it has a multiplicity of 2 because it's repeated twice or occurs twice. Last but not least, the intercept at x equals to -1, which is this one right here, is the repeated solution of the factor x plus 1 all cubed equals to 0. You notice how the graph passes through the axis at the intercept, but flattens out a bit first. See here? It passes through, however, it doesn't pass as a line, as you can see here. It flattens a little bit as it passes, as you can see there. Okay? This factor is cubic. This factor is cubic, meaning degree 3. So the behavior near the intercept is like that of a cubic function, with the same S shape near the intercept as the toolkit function f of x equals to x cubed. Here, the cube function, similar to it. We know that the cube function is going to behave like that, or like this if it's negative. Okay, we call this a triple 0, or a 0 with multiplicity 3. So multiplicity 3, 0. For zeros with even multiplicities, in general, the graph is going to touch or tangent to the x-axis. They're going to touch and bounce, similar to this behavior right here. For zeros with odd multiplicities, the graphs cross or intercept the x-axis in this manner right here. With graphs multiplicity 1, it's going to pass as a line. If it's a multiplicity that is odd bigger than 1, then the graph is going to flatten a little bit before it crosses, or it's going to behave as a cubic function. So hopefully these shapes illustrate the types of multiplicities that we have and the behavior of the graph at that intercept. That will lead us to the next concept that is going to help us graph the polynomials. So another observation of the behavior of the graph of the polynomial functions, the end behavior. The end behavior is going to help us combine with what we learned about the zeros and their multiplicities to graph the polynomial functions. As we pointed out when discussing quadratic equations, when the leading term of a polynomial function is an even power function, as x increases or decreases without bound, f of x increases without bound, which means the end behavior of the function is going to look like this, or it's going to look like that, depending on the leading coefficient, if it's positive or negative. If it's positive, then when x goes to positive infinity, also f of x goes to positive infinity, and when x goes to negative infinity, or on the left side of x, f of x goes to positive infinity. If the leading coefficient was negative, then when on the right side of x, f of x is going to go to negative infinity, and on the left right of x axis, f of x is going to go to negative infinity as well, which means both arms are going in the same direction. That is if the power is even. When the leading term is odd power, then we have two types of behaviors in this case. So as x increases without bound or goes to positive infinity, f of x also decreases without bound. As x increases without bound, f of x also increases without bound. If the leading term is negative, however, it will change the direction of the end behavior here. If the leading coefficient is positive and the degree of the leading term is odd, the behavior is going to look like this. On the positive side of x, the function is going to go to positive infinity or goes up this way. On the negative side of x, the function goes down. If the leading coefficient is negative, then on the positive side of x, the function is going to go down. And on the negative side of x, the function will go up. You can understand that by, if this is positive, the leading coefficient is positive, the behavior is increasing. If the leading coefficient is negative, the behavior is decreasing. So you can remember that with increasing and decreasing based on the sign of the leading coefficient. So these are the end behaviors that we're gonna talk about. Again, what happens in the middle is exactly what we're going to find out using the information we learned from the zeros and their multiplicities. So again, what happens in the middle, we're gonna find out combining the information we have from the multiplicities of the zeros, the end behavior, and the turning points, and the relationship between turning points and the graphs and the degree of the polynomial. So to recap, if the degree is even, we're going to have any of these two behaviors depending on whether the leading coefficient is positive or negative. If it's positive, two arms up. If it's negative, two arms down. If the degree is odd, then if the leading coefficient is positive, we're going to have an increasing polynomial behavior. If the leading coefficient is negative, we're going to have decreasing behavior. One arm up, one arm down, one arm up, one arm down. Understanding the relationship between degree and turning points. In addition to the end behavior, recall that we can analyze the polynomial function's local behavior. It may have a turning point where the graph changes from increasing to decreasing, rising or falling, or decreasing to increasing, falling to rising. If you look at the graph of the polynomial function, I believe there is an x to the fourth here, minus x cubed minus 4x squared plus 4x, you will see that it has this graph right here. The graph, as you can see here, has three turning points. Here is 1, here is 2, here is 3. This function is a fourth degree polynomial. This function f is a fourth degree polynomial, and it has three turning points. The maximum number of turning points of a polynomial function is always one less than the degree of the function, just like we learned previously. So we can find from the degree of the polynomial, we can find the number of turning points. If we have the number of turning points, we can determine the degree of the polynomial. So here is our first example. We're going to use all of the information we learned so far combined with one another in order to determine the equation of this graph right here. So the question says, write a formula for the polynomial function. So the first thing I'm going to look at is the x-intercepts. I noticed that this function has three x-intercepts. It has a y-intercept at 0 and -2. So if you look at the first x-intercept, which is x minus 3, so I'm going to say x minus 3, that is the, x equals minus 3. This has a multiplicity of 1 because the behavior of the graph is similar to a behavior of a linear. So I'm going to say this has a multiplicity of 1, which means if I turn this into a factor, meaning I want the right-hand side to be 0, I'm going to add 3 to both sides. I will end up with x minus x plus 3 equals to 0, and that is my first factor, basically. The next intercept that I notice here, which is x equals to 5, also has a multiplicity of 1. So x equals to 5 has a multiplicity of 1 as well, which means if I turn this into a factor, it's going to be x minus 5 equals to 0. When x is equal to 2, however, notice this one right here, the graph touches and bounces. So the behavior here is the behavior of quadratic. The behavior here is a behavior of quadratic. So I'm going to say x equals 2 has a multiplicity of, let me see here, before I decide whether it is 2 or 4 or another even number, I need to determine the degree of this polynomial first. So by looking at this graph has 3 turning points, which means the degree is turning points plus 1. So I'm going to say the degree here at the beginning is actually 4. So I have 2 here, and then the multiplicity is going to be 2. It's not 4, so it's going to be 2. So to write the factor, it's going to be x minus 2, and I will raise the factor to the second power because of its multiplicity. So now I can rewrite the function f of x equals to some leading coefficient that I do not know what it is, times the first factor, times the second factor, times the third factor. In order to find a, I'm going to utilize what I have. So what I have here is I have the y-intercept. The y-intercept is 0 and -2. So I'm going to plug that in here. So I will use the point 0 and -2 to find a. That means when x is 0, f of x will be -2. So I'm going to substitute -2 equals a times 0 plus 3 times 0 minus 5 times 0 minus 2 all squared, which will lead to -2 equals to a times 3 times -5 times 4. That is -2 equals to -15 times 4, -60a. We're going to divide both sides by -60. So we have a equals 1 over 30. So the final answer, I'm going to write it here. F of x is equal to 1 over 30, x plus 3 times x minus 2 all squared times x minus 5. It doesn't matter how you order these factors, by the way. So I have all of the steps here, and the final answer is stated here as well with some explanation.